Hello everyone. In this video, I'm going to walk you through news vendor problem. In the previous video, we talked about EOQ model, which is a fundamental inventory management model for managing inventory of products that have a long life cycle. These are products that, again, you have heard this many times. I'm going to repeat it again. You have a longer, very long selling season. If you don't sell it today, you can sell it tomorrow. However, there are some products that don't have that properties. All right, they just have a very short life cycle. Because they have a short life cycle, they then you don't really your concern about their management is not inventory ordering cost or inventory holding cost. Your concern is mostly making most money out of in that short selling season, or making sure that majority of customers are going to get the product if they are looking for the product. All right, so let's see a few examples. So we're going to talk about news vendor problem. So imagine this situation where you are buying newspaper for 70 cents, you are selling it for $1 in second floor lobby or in an atrium, and if you don't sell the product by the end of the day, you have to salvage it at 10 cents or $0.1, right? Now, in today's newspaper, you cannot sell it, you cannot keep it for tomorrow, you cannot sell it for tomorrow. This is what I mean by short selling season. Today's newspaper is good for today. It has, let's say, 24 hours or even less than that selling season. You have to make inventory decision. If you are selling newspaper in the atrium, second floor lobby, you have to buy newspaper somewhere. All right, you are gonna make inventory decisions. How many you are gonna buy, we don't know, because you don't know how many you are gonna sell, right? And then you are gonna realize uncertain demand. Once you make the inventory decision, that time frame is very critical. You have to make inventory decision before realizing uncertain demand. Is that realistic? In a lot of practical situations, that's exactly what happens, right? And then, and only then, you will have the luxury of evaluating inventory decisions, all right? Um, I'm going to pause here and talk a little bit about difference between this and this model and EOQ model. Everyone, in EOQ model, we had rate of demand, or in previous example, it was 600 units per week. We don't have that here. You don't know exactly demand rate. We have some information about it, but it's not as deterministic and certain as EOQ model. All right, and that's the beauty of this model. It's going to be, we are going to add uncertainty in making inventory decisions, because that's exactly what happens in real world. All right, what are the situations that this kind of time frame of making decision, then on realizing and then realizing uncertain demand, then evaluating your decision, this time frame, where else does it show up? Pretty much everywhere in inventory decision making, this shows up. Because think about it, if I know demand before making inventory decision, let me repeat myself. If I know demand before making inventory decision, then there is no decision making. I know the demand, so I am going to store inventory equal to demand. When I flip the time frame, that's when problem becomes more realistic and more exciting. So here are the first example we talked about, newspaper problem. All right. Here's another one. If you remember from day one of the class, we talked about flu shot production. Flu season starts roughly around October, late September, October, and then goes on until roughly around March, right? So that is a selling season for flu shots. But when these manufacturers, pharmaceutical companies, they have to produce flu shot. They have to start planning production of flu shots 8 to 9 months before start of selling season. That brings us from September, October. If you go 8 9 months back, you are going to get to sort of middle of one flu season. You have to start planning for production of flu shots for the next year, right? because of that very long production cycle, very long production time. Once you make commitment that this year I'm going to produce, let's say, 50 million shots of flu shots, you cannot change that easily during the season. You cannot change it because that requires preparation, that requires preparing raw material, and raw material for production of flu vaccine is the chicken eggs. All right, so you have to start planning for all of that 8 9 months in advance, and once you make that commitment again, it's going to be very difficult to change it. And if you realize, let's say in August, you realize that, you know what, oh, we need 20 more million shots, even if you start in August, the flu shots are not going to become available on time. All right. This is a perfect news vendor problem. You have to make inventory decision about production quantity before flu season, and you get to make that decision only one time. And you make that decision only one time for that specific selling season, simply because that production cycle is much longer than your flu season, or your selling season in this case. All right. I'm sure by now you noticed that, oh, this could be a sort of a inventory model um, for seasonal products. And if you got that feeling, you're 100% right. The seasonal products have that nature. Other example, this one is a very lame example I've taken from somewhere. I'm not going to tell you where, but you can go over it yourself. There are two other seasonal products that I'm going to talk about them: turkey for Thanksgiving season, and Christmas tree for Christmas season. Both of these cases, retailers usually make commitment, make orders in advance, and because selling season is such a short season, consider turkey for Thanksgiving. It's just a couple of weeks, right, roughly. It usually is difficult to uh, significantly change your inventory decision in the middle of selling season. All right. It's the same thing with Christmas tree. Here's another example that is a little bit different than what we have discussed in the class so far. Imagine you have a flight that imagine you have to be in the airport by exactly 8:30 a.m., not 8:31, exactly 8:30 a.m. Right? If you leave at 5 a.m., you have left yourself 3.5 hours of inventory of time. Now, we are looking at the time as an inventory now. How is this relevant? Well, you don't know how long it is going to take you to get to the airport. Demand for time is uncertain, but you have to make a supply decision before observing uncertain demand. That time to get to airport can be half an hour. It can turn into a 2.5 hour travel. All right. You don't know that. Now, in these kind of situations, they usually are at least two competing forces, two forces that usually in going extreme in either one of them is not ideal. Well, what do I mean by competing forces? In the case of leaving to airport, you can leave at 1 a.m. and guaranteed you're going to be there right on time. But then you're going to lose one night of sleep. You can also sleep until 7:30 a.m. and leave right at, let's say, 7:45. Then you are leaving yourself exactly 45 minutes of supply of time. That's very risky. Yes, you had a good night's sleep, but now you are risking missing your flight. All right. So two end of the extreme, none of them is ideal. We are looking for that sort of happy medium in the middle. What is the right inventory decision? Another business problem that is not listed here, but I want to mention it on the go is imagine you are purchasing a supply from a product from a supplier in China, and because of type of contract that you have with supplier, that requires you to commit to inventory 6 months in advance. That's a typical contract with Chinese suppliers. Do you know demand in advance? No, you don't know that. Especially if product is a seasonal product, especially if product has a little bit of flavor of a fashion industry, then that becomes a lot more. It becomes a lot more complicated problem. You have to make inventory decision before observing uncertain demand. And because of that long production cycle, in this case, I mentioned 6 months, it's very, very difficult, almost impossible to change your inventory decision in the middle of the season. I'm going to go on tangent a little bit. It has nothing to do with slides. If near Christmas season, let's say if you 2 3 months before Christmas season, that's a little bit extreme, but it's I've seen companies do that, at least pre-COVID. Um, the companies that sell specific seasonal, especially toys, what they do, they say if you pre-order, you get this much discount. Why do you think they are offering discount for pre-order? By offering discount to get pre-order, they are reducing uncertainty from demand. They lock in that 1 unit of demand and make sure that, okay, you know what, that 1 unit of uncertainty is gone. All right, that sort of practice of pre-ordering, even at a discount a little bit, it removes uncertainty from customers' demand. All right, so back to our slides. These are assumptions that we have for news vendor problem that we are going to discuss. We assume that demand is not constant, it's practical. We assume that we have distribution on demand. This is one of the questionable assumptions that we have for this model. Sometimes you can say, yes, I have a reasonable distribution for demand. Sometimes not so much. All right. Next, we assume that product becomes obsolete. This is actually pretty reasonable in this context. We assume that you have to place order before start of the selling season, and yes, that is reasonable. We also assume that you get to purchase only one time for that one selling season. Again, in a lot of practical situations, that actually is not a very unrealistic assumption. Now, we are going to learn this problem mostly this model. We are going to build and learn this model in the context of this problem that you see right here. So if you read the problem, it says demand has normally distributed with average of 400 and standard deviation of 50. You buy the product for let me see, you buy the product for 20 cents, you sell it for 50, no, you sell it for 80 cents, and its salvage value is 5 cents. Meaning if you don't sell the product, any leftover product is going to be sold at 5 cents. Of course, that salvage value, 5 cents, is below the price that you have paid for the product. All right. Now, the question is, how much should I order at the beginning of, how much inventory should I have at the beginning of selling season? These are the specific steps for implementing this model. First, we need to generate or gather economic data. Then we are going to have a demand model. Don't let this busy slide intimidate you. This is a very, very straightforward process. Then we are going to have decide about our objective function. There are two types of objective functions. One type, maximize expected profit. The other one is satisfy specific fill rate. We are going to get there. And finally, decide about the quantity. All right. This step, as you see, there's a lot of writing here, generated demand model. This is the most challenging part of building this model. How do you generate, how do you model, how do you quantify uncertain demand? The easiest, most straightforward way of doing that is by hopefully using historical data to find the distribution of demand. In other words, use probability distributions for modeling uncertainty in demand. Demand is normally distributed, demand is exponentially distributed or uniformly distributed, all of that. All right. But that's not the only way of doing that. There are other ways of building demand model. Again, that is the most challenging part of this problem. We are going to stay with the just probability distributions, but I want you to know that there is a lot more happening in that domain. All right. Let's start with in our problem of that sweet cider problem. Let's start with gathering economic data. We pay 80 cents for the product. We pay 80 cents for the product. We pay 20 cents for it. We sell it for 80 cents, and any leftover inventory is going to be salvaged at 5 cents. That was step one. Gather economic data. That was step one. Step two, generate demand model. We are here for the sake of at least simplicity here. We are going to say, you know what, demand based on historical data, we fit a distribution to this demand, and it is normally distributed with an average of 400 and a standard deviation of 50. All right, that is a demand model. Demand is normally distributed with an average of 400 and a standard deviation of 50. What does that mean? Let me just pause here and make sure I explain this a little bit. It means demand can take I'm sure you have seen this bell curve many times in the past. This is what it means, that on x-axis you have values of demand. Demand can take any value on x-axis, and on y-axis, what is that curve? On y-axis, I have relative likelihood. Likelihood, right? This is not necessarily probability, but just the likelihood of something happening. All you can say is that values around average right here have higher likelihood of values on tail side. All right, so the height of this curve at any point is the likelihood or chance of that event, that one unit or that one quantity or that one the specific value of demand happening. Step number three, let's talk about the objective function. A lot of times you want to make inventory decisions in a way that it maximizes your expected profit or minimizes your expected cost. First, we are going to start with that. But in some situations, you don't care about your profit. Let's say you are new to a market and you are willing to take some hit, they make no money, but penetrate that specific market. Make sure that customer knows about your brand, knows about your product. There, you don't care about the cost. You just want to make sure that if customer wants my product, he's gonna get it or she's gonna get the product. All right, that is gonna be the next objective function that we are gonna discuss. Last one, to meet the target in stock probability. We are gonna talk about this later, but first let's focus on situation where all you care about is money. I want to maximize my average profit or minimize my average cost. All right, so let's talk about that objective function. How are we going to make inventory decisions that knowing about the problem setup and knowing that all I care about is non-profit? Well, what are the, again, when we are trying to maximize profit in any optimization problem, you're going to have at least two competing forces, right? Here, those competing forces are ordering too much versus ordering too little, having too much inventory versus having too little inventory. All right, if you order a lot of inventory, the good thing is that if any customer wants for the demand, for a product, you have it. Bad thing is that you probably are going to end up paying a lot of salvage. In other words, you are going to end up salvaging a lot of your product. If you order too little inventory, good thing is that most likely you are not going to salvage your product. But the bad thing, negative thing, is that you are going to probably not have enough inventory for everyone. All right. So again, the question is, what is the happy medium somewhere in the middle? Now, how are we going to model that having too much inventory versus too little inventory? We are going to introduce two parameters. One of them is called CO, cost of overage, and the other one, CU, cost of underage. These are very simple concepts, extremely simple concepts. I just hope that we are not going to end up memorizing them, right? Because they might be slightly different for every problem. So let's talk about CO first, cost of overage. CO is this is the situation you are in. Imagine you sell everything and there is only 1 unit of inventory left at the end of selling season. Just 1 unit. All right. How much is that going to cost you? Well, that 1 unit, you paid already 20 cents. You've already paid for it. But you are going to sell it at 5 cents. You are going to salvage it at 5 cents. And that means its cost for you is going to be 15 cents. All right, that's simple. How about let's go to the cost of not having enough inventory. Let's say there is demand for your product, you sell everything that you have, and right at the end of selling season, there is one customer that says, hey, I want 1 unit, but you don't have that. You don't have that. You run out of inventory, and you are not able to sell one unit to the very last customer. How much cost are you going to incur? Well, cost is going to be you could have sold it for 80 cents, but you had to pay 20 cents for it to begin with, right? So it's going to be 80 minus 20, 60 cents. That's it. So it's so easy to write formulas for these parameters, but that is not a good idea. So just remember these two concepts the way they are, and the rest of it is going to make perfect sense. All right. Now, now that I have those, the rest, these three slides, this one and this one and this one, these three slides, they're a little bit quantitative and talks about, how we can get to the formula that is in the next page. So I'm going to avoid getting to too much of details and explain the logic here. All right. The logic of formula that you are going to see in the next page is this is how we are going to find it. Well, there are two competing forces. All right. One of them is having too much inventory. The other one is too little inventory. What you have here, the blue line that you have here, this is this is a marginal gain that we are going to have if I switch. For example, if I switch from this level of inventory to the next one, from Q to Q plus 1. All right. If I switch from this Q to one after that to Q plus 1, how much gain am I going to have? It's that height right there. How much loss am I going to have? It's this much, right? The height of that red line. Well, as long as my marginal gain is more than my marginal loss, I'm fine. All right. So by increasing Q, those numbers, those two curves are going to converge to each other at some point. You do not have any incentive to increase your inventory level, because if you go to the right, your marginal if you go to right, your marginal gain are going to go below your marginal loss, and to the left you are leaving money on table. So at this point right here, where marginal gain and marginal loss, they are the same, at that point I'm going to stop and say that is my right inventory level. All right, I have no incentive to deviate from that point. Again, there's a little bit of math involved, but we are not going to get into too much of a math. If I solve that problem of marginal gain is equal to marginal loss, it's going to take me to this equation, and quite frankly, we don't need to get into too much of how we got those quantities. Finally, we are going to get to how we can find a Q. If I'm looking for inventory level Q star must satisfy this equation. Cumulative distribution function, capital letter F, at Q must be equal to Cu over Cu plus Co. All right. Again, what is CDF, cumulative distribution function? This comes from probability and statistics course. We are going to review that one as well. Let's focus on this one, Cu over Cu plus Co. This has this is known as a critical ratio. And you have that right here as well. Another name for it is called service level. All right, your handout uses critical ratio. I'm going to, just to make up for it, I'm going to keep using service level as well. All right, let's do a little bit of a calculation, and I'm going to explain that service level, why it's called service level. I'm going to explain it there. All right, let's go to this our problem that we have. Cost of underage, let me make sure. Cost of underage is 60. All right, that needs to be fixed. 60. Cost of overage is 15. Right, and my critical ratio is going to be Cu over Cu plus Co. All right, that's what I have here. Cu over Cu plus Co. Right, that is 60 divided by 60 plus 15. That's going to take me get me to 80%. Or 0.8. What does that mean? Let's have an intuitive explanation about that. What that means is that if you really want to maximize your profit or minimize your cost, you do not need to satisfy 100% of customers' demand. You just need to have enough inventory that is going to satisfy 80% of customers' demand. Why not shoot for 100%? Well, because demand is uncertain, because demand is uncertain, uh, there is always a chance of, if you have too much inventory, there's always chance of ending up with extra inventory that is going to cost us a lot of that you have to salvage a lot of inventory, and that is not cheap. All right, the middle point that is going to balance off the cost of too much inventory versus too little inventory is a point where you try to satisfy 80% of customers' demand, not more, not less. Now that I want to satisfy 80% of customers' demand, what quantity is going to give me that? All right. That is where demand function comes into play. Now, on x-axis, I have demand values. Demand values are on x-axis. That 400 is that 400 right there is your average value of demand, right? So demand is normally distributed with a mu of 400 and sigma of 50. We know that from problem statement, right? This is the shape of normal distribution. Area under normal curve up to 400 is 0.5. Area after 400 is also 0.5. If you want to satisfy 80% of customers' demand, I need to store enough inventory. I'm going to call that Q. That probability that demand exceeds that quantity is only 20%. Right there, that area is 20%. And probability that demand is going to be below that quantity, this one is 80%. That's why it's called service level. You are providing service, you are storing enough inventory that is going to provide service to only 80% of customers. The other 20%, you are gonna, on average, you are gonna lose 20% of customers' demand. Again, you are caring about cost, and you are caring about you care about maximizing your profit or minimizing your cost, nothing else. All right. So if that 80% is, oh my God, I'm going to lose 20% of customers' demand, well, that is your objective. If your objective is to maximize profit, this is the solution. Well, how can I find that Q? This is a little bit of a too much of a math or too much of a probability and statistics. I thought I'm done with probability. You're never done with probability and statistics, especially if you are in analytics area. All right. How can I find that Q? You can use at risk, which is a software I teach for in simulation course. That one is not an option here. All right. But I just put it there so that they tell you that's one way of finding it. Another way of finding it is using normal tables or Excel functions. Quite frankly, normal tables, I show it to students in class. I give them option of using normal tables, but now that we have Excel, there's no point of forcing students to use normal tables. But nonetheless, if you want to use normal tables, be my guest. My expectation from you in exam is to be able to write proper Excel formulas. That is my expectation. All right. Now, there are two ways that you can do this with Excel. One of them is using norm_inv function. The other one is norm_s_inv function. That S stands for standard normal. All right. Let's look at norm_inv function as well. My expectation is that you know both of them. Right. That is the expectation. Norm_inv, this is a syntax. Norm_inv of critical fractile or service level, in this case, is going to be 80%, comma mu 400, comma sigma 50. All right. And that's going to give you, if you type equal norm_inv of 0.8, comma 400, comma 50 in Excel, it's going to give you 442. That is your quantity right there. This is 442.8. Another way of doing it in Excel, which is very, very intuitive, and I like this one, quite frankly, a lot more, is using norm_s_in function. Right. First, we are going to find z value. All right. Z value is going to be norm_s_inv of critical fractile or service level. Then we are going to use mu plus z sigma. Mu is 400 plus z is right there, norm_s_inv of 0.8 times 50. It's going to give you the same thing. All right. Why did I why did I write it in this format? Because there's a very nice interpretation behind that. All right. When Q star, we write Q star equal to mu plus Z sigma. This mu is average demand. We are saying, listen, my order quantity has two components. One part is average demand. I want to make sure that I cover the average demand plus Z sigma. This is your safety stock or safety inventory. All right. Say I add something. Most of the time we add, sometimes you subtract as well, right? Because this Z could be a negative number as well. Mu plus Z sigma. This is my safety stock, something on top of average demand. That safety stock has two components. It says, listen, if your demand is very uncertain, by increasing sigma, you have to have higher safety stock. In one of the classes, one of the students asked, how do we determine safety stock? There you go. It has two elements. One of them is standard deviation of demand. By increasing standard deviation of demand, you are going to have carry more safety inventory, because you want to cover yourself, and increased variability is going to you have to pay a little bit extra cost to protect yourself against variability. That's one. And the other component of safety level or safety stock is a Z. That Z, remember, is equal to norm S inv of critical fractile. Another name for this critical fractile was service level. Service level, right? By increasing service level, norm S inv is going to increase. As a result, you are going to need a lot more safety stock. All right. So your ordering quantity is a function of, has two components. One is average demand, mu. The other component is Z sigma. That is your safety stock. Safety stock is a function of two factors. One is amount of variability in demand. By increasing variability in demand, or sigma, you have to carry higher safety levels, safety stocks. All right, that makes sense intuitively. The other factor that dictates safety stock is your service level. How much of a service level are you willing to provide for customer? Higher service level means that you have to carry more inventory and more safety stock. All right. Now, again, expectation is that you know both of these formulas, Excel formulas, and you know there's a proper syntax, and you're able to use them. Now, so far we have talked about continuous demand. How about discrete demand? Is it possible to have discrete value for demand? Yes, it is possible, and this example is going to provide us exactly that. All right. If you read the problem, it says we are selling cards for Christmas, and these are the possible values of demand: 125K, 175, 225, 275, 325, 375, and 425. There's nothing in between. Those are all possible values of demand. What are the probabilities of each of those? Those are probabilities. There's a probability of 10% probability that I'm going to have demand equal to 125K. There is a 15% chance that my demand is going to be that much, and so on and so forth. All right. You see that in this case, demand is discrete. Demand is not continuous like previous example, which was a normal distribution. All right. In this case, how do we solve the problem? It's very, very, very similar. All right. So let's write down economical data that we have here. Price of the product is 65 cents. We pay 30 cents for it, and there it doesn't have any salvage value. All right. Cost of overage. If I end up with extra inventory, but I'm not going to sell it for anything because salvage value is 0, and I'm just paying 30 cents for it. What is cost of underage? If you don't have enough inventory, you are going to lose the opportunity of making 35 cents. That brings me to from here we can calculate critical ratio. I have calculated right here, but I'm going to write it here as well. CU, which is 35 over CU plus CO, 35 plus 30, that's going to bring me to 538 or 53.8%. All right. Now, next step, now that I have critical ratio, next step is to build my CDF or cumulative distribution function. For the very first one is going to be 10 point one, I'm sorry, 10% or point one. Second one is going to be sum of these two, which is going to be 0.25. Third one is going to be sum of these three, which is going to be 0.45. Next one is going to be sum of these four. Cumulative distribution function is going to be 0.7, and the last one is going to be 1, right? Now, starting from the very last one, which is 1, I'm going to compare each of these with my critical ratio. Is 1 bigger than or equal to 553.8? Yes, it is. So I'm going to go all the way down. I'm going to go all the way down, all right, until I hit that, or the one that is the smallest number that is larger than that. All right, so I know that's confusing a little bit. I'm going to say it one more time. Either I have to hit exactly that number, or I'm going to stop at the number that is the smallest number larger than or equal to 53.8%. So smallest number that is larger than or equal to 53.8 is right here. All right, and that means that my quantity, ordering quantity, is going to be equal to 275 right there. Right, that's why I have Q star equal to 275K. Now, there's one last topic left, and that is what if my objective is to meet a certain fill rate or service level? What if I don't care about profit? What if I want to store enough inventory that is going to satisfy 99.9% of customers' demand? And that happens a lot if you are trying to penetrate a market. You want to make sure that customer wants a product whenever customer gets product whenever they want it, right? In that case, there is nothing new. So what we are going to do, it's even easier. It turns into a probability and statistics question. In sweet cider problem, the problem that we discussed earlier, assume that you want to satisfy 99% of customers' demand. It says my in-stock rate must be 99%, meaning I want to have enough inventory that it has a 99% chance of satisfying all customers' demand, or equivalently, it is going to satisfy 99% of customers' demand. All right. In that case, a normal distribution, a normal table that we have, a normal curve that we have here, I'm looking for that number right there on x-axis. That one, I don't know what that is. That area up to that point is 99%, and area after that point is 1%. All right, so well, first I need to find z, and then use mu plus z sigma. Mu is 400, I know that. Sigma is 50, I know that. Z is going to be norm S inv of this area right here, this area up to that point, 99%. That is going to bring me 516.31, right? If I want to satisfy 99% of customers' demand, I have to store 516.31 units. Let me just compare that with situation where we satisfied only 80% of customers' demand. Remember, we satisfied only 80% of customers' demand, and it says, you know what, if you want to satisfy 80% of customers' demand, which is, by the way, is going to minimize your cost or maximize your profit, you only need 442 units of inventory. Now that I am amping up my service level, percentage of customers' demand that I want to satisfy from 80% to 99%, this says that you have to store a lot more inventory. All right. All right. Let me see. I think I've talked about all of these throughout this video. I'm going to just pause here. I don't want to spend more time on this, but again, this is another. I'm going to end this section with another application that you are trying to create capacity for a product that has a potential, but you don't know if it is going to be, if it has 100% chance of success. All right. There is a potential, but you are not sure. But you have to make an inventory decision or capacity decision right now. How much capacity are you going to create? You don't know if the product is going to succeed. All right. The time frame is the same as time frame of news vendor problem. All right. You have to make capacity decision now without knowing if product is going to be 100% success. There's a chance of a product not succeeding as well. All right. Again, I brought this up. I'm ending with this specific example because I want you to know that even though that's a very simplistic, simple model, not a difficult model, very simple model, but a lot of practical problems, their time frame fits in the time frame of news vendor problem. Just be mindful of that. All right. With that, I'm going to stop. I'll see you guys in class.